Guys, we're starting. Are there any questions? Okay, just let me start with a little announcement. We have the exam on Wednesday, as you know. And what time did we start last time? We started a little early.
10:15.
So we'll start again at 10:15 if that works for everybody. So that way you'll have a little bit of extra time. Again, I show up for the exam, so that means I'm here to answer questions. I don't just send the TA. Again, so we don't waste time, spread out, no one in front of you, behind you. So the nearest neighbor chair should be empty. And I will check your stuff. And again, whatever you have printed out, you're allowed your textbook and your class notes. They have to be properly bound. Not 3 pages stapled together and another 5 pages stapled together. In a loose leaf or in some sort of binder. They have to be bound. Yes?
You don't have a loose leaf with a transport table?
The one I gave, yeah, that should be in there also. Yeah, sure. If I hand it out in class, you can certainly bring that. In the first exam, there are people who didn't understand what bound meant. Now, I think I explained it, what bound meant. So whereas I let people get by with stuff last time that wasn't properly bound, I won't do it the second time. Because you should know by now what bound means. Okay. Are there any questions? Okay, well, we had a little hiatus because of the meeting. We had an extra class the week before and a half a class during the meeting where I went through Simulink. I would advise you to use Simulink, practice a lot on it because it'll give you some insight. You can change parameters, see what happens. And the examples you do in class, you can then look on Simulink and try to see what the numerics give you, and that'll give you some insight. And as we analyze stability more and control, it'll be more and more useful to use Simulink. Okay, so as we noted in the last class before the meeting, the SAG meeting, we finally got to control. We spent a good part of the semester learning how to do modeling and how to analyze models, time-dependent models, and how to analyze them, both with standard ODE methods as well as Laplace transform methods. The Laplace transform methods were a bit more involved, but for a given problem, they were much easier, and they gave you a lot of information, often without even needing to invert the Laplace transform. So we started finally looking at control, and not just modeling. So if anything, this course should have been called, rather than just being process control, we should have, if we were honest, we would have called it unsteady state modeling and control. Because we spent more than half the semester doing unsteady state modeling, which is needed for control because when you're controlling the system, it's not steady. It's changing. So we started by identifying variables. We identified the control variable, or variables, the things we want to control. So in a reactor, we might want to control the conversion or the product composition, etc. We also identified the manipulated variables. For each control variable, we wanted to have at least one other variable that we can manipulate that will have an effect on the control variable, a direct effect and a large effect. So we have control variables, manipulated variables, and something else. And we also look at disturbance variables. Variables where there are often disturbances that then perturb the problem. So these are the variables. And we generally identify these variables before we build the plant. So we make sure we have sensors in the right place to measure everything we need to measure. And that we put in enough manipulated variables to control the control variables. Now, any sort of control is based on the error. And we have various measures of the error. So we have the integral error, IE, integral error, was the integral of e of t dt from 0 to t. And that's the integral of the error, where I should mention where e of t is defined as the set point minus for the control variable minus the control variable. So it's the value of the set point minus the control variable, and if the control variable equals the set point, then the error is 0. So the integral error is this, and the problem with this is if I take the integral, then positive deviations cancel negative deviations. So that would make it look like there wasn't a problem, even though sometimes it's too high, sometimes it's too low. So we don't like this one. This one's bad. But we can look at the integral absolute error, which is the integral from 0 to t prime, the absolute value of e of t prime dt prime. And that, there the negatives don't cancel the positives anymore. Or similarly, I could use the integral square error, which is the integral from 0 to t prime, e of t prime, quantity squared, dt prime. So both of these are good because they get rid of negatives and positives canceling each other. Sometimes I want to, when I really want things to go to 0 at long times, I want to stress the long time more than the short time, and then I could look at IT AE, which is the integral from 0 to t prime of t times the absolute value of e of t prime dt prime, 0 to t. So there I'm multiplying t times the error, and that tells me that at long times this thing had better go to 0, otherwise this thing's going to explode. So these are all different measures of the error, and I could do my control based on any one of these three. Now, what are my goals? Well, the first goal is I want e of t to go to 0. I want the difference between the set point and the value of the control variable to go to 0, and I want it to go to 0 quickly. I don't want it to take the age of the universe for it to go to 0. There are other things I want to go to 0. So in particular, I want the offset to go to 0. As we'll see, that's not a trivial statement. That is, sometimes you could have the set point here, and the control variable might do some funny things, but it never quite goes to the set point. There is a steady state difference between the set point and the value of the control variable that could happen. And when I say I want the offset to go to 0, it means I don't want that to happen. I want the error to go to 0. There are various other measures. One of them is called the rise time and the decay ratio. So the rise time. I want a small rise time. The rise time is, let's say this is time, here's the set point. And at t is equal to 0, I changed something. There was some disturbance in the system. So after the disturbance, the control kicks in, and it's going to take some time for the control variable to get to the set point. Now it may overshoot and come down, for example, or it might go directly there. But the rise time is the amount of time it takes, this is the rise time, to cross the set point the first time. It may not stay there, but it's the amount of time it takes to get there for the first time. That's called the rise time, and I want the rise time to be not too big. Then I have a decay ratio. I want that thing to also, so what's the decay ratio? So if this is the set point, and here I have t equals 0, and something funny happens at 0, here's a control variable, and let's say it oscillates. The decay ratio is the ratio of the first peak to the second peak, the second peak to the first peak. So it's the ratio of A to B. So I can define it as A over B over B over A. Let's define it as B over A. I want B over A to be small. That is, if it's going to oscillate and decay, I want it to decay quickly. So that's the decay ratio. Some other terminology. Settling time and manipulated overshoot. Okay. The settling time I want this to be small. So what's the settling time? So let's look at the similar situation, 0t. And so this is a stable situation, and what's the settling time? Let's say I have, this is a 5% bound. This is plus or minus 5% of the set point. So the settling time is the time it's the time after which you're always within 5% of the set point. You may not have gotten to the set point, but you never get more than 5% away. So it's the amount of time it takes to get to a situation where you never exceed 5% again, away from the set point time. And finally, there is the manipulated overshoot. And you want this to also be small. So what is the manipulated overshoot? Now remember, you've got your control variables and your manipulated variables. The manipulated variables are what your controller changes. So the manipulated variable is the manipulated variable as a function of time minus its value at infinity divided by its value at infinity. So its value at infinity might be a certain value, and you want to know what percentage does it go over and under its infinite value. So it's the percentage that it overshoots or undershoots. And so here I plotted the control variable, but the manipulated variable is doing all sorts of stuff also. So remember, here I have the control variable, but at the same time I have the manipulated variable that's doing things to get the control variable to go to that value. So let's remember the manipulated variable might be doing something different. The manipulated variable might be doing something like this. It's moving around. Empty. So the control variable doesn't just go like this on its own. I have to have a manipulated variable to get it to go there. So MV, I also want to keep track of MV. Now, the fluctuations in the control variable and the manipulated variable are both important. We not only want to keep the control variable not varying too wildly, we don't want the manipulated variable to vary too wildly either, because every time we vary the manipulated variable, there's some valves going, and if you constantly open and close valves, eventually they break. So those are things that we want to make sure don't happen. Those are our goals.
Actually, I have two questions. One is, can you define offset?
Okay, the offset, again, is the long time difference between the control variable and the set point. So, for example, t, if this is the set point, and this is the control variable here, and here's 0, t, so is if there's a difference at long times, that's called the offset.
And then my other question is, when you're talking about the decay ratio, the ratio of that d distance, that a distance
Well, that's what you hope, yeah. I mean, if you, put it this way, typically when things are linear, then you have an oscillation multiplied by an exponential. And if it's an exponential at regular distances, then you've got, so the decay ratio, you have a certain value, and let's say this is the period. Let's call the period delta t. Then you typically, at a value, you have a certain value here, say e to the at minus at versus e to the minus at plus delta t. So this would be B over A. So you can see what that will give me. That'll give me e to the minus delta t and e to the minus a delta t. And notice that's independent of where I started, of t. So as long, if I have this exponential decay, then in fact, and the period is constant, then the ratio will always be the same. It only depends on the period. So that's a very good question. Other questions? Okay, so what I'd like to do is just go through an example that we're going to use for control. And before I do the example, I want to do a sub-example because I'm going to use it. We typically use valves. And I would like to know how the flow rate, so this is sort of an aside example, how does the flow rate depend on the valve position? Because we're going to constantly be using that, so why don't we just get that out of the way. In order to do that, we're going to go appeal to the energy, mechanical energy balance from unit ops. Of course, I didn't memorize, so let's copy it down. And that's delta u squared over 2 plus g delta z plus the integral dp over rho plus shaft work plus the integral ev, which is equal to 0, where ev is equal to 2 fl u squared over g. Let's figure out what these things are. Okay, so here we can look at, we have a pipe and we have some sort of valve here. And the valve can close when this is all the way down, or it can open. So u is the average mean velocity. So this could be u. And I have u here as well. This is u1 and this is u2. And over here I have u3. u1 again by continuity, if the diameters are the same. Okay, and typically this is horizontal. So I'm going to ignore delta z. Yes?
Quick question. What is the last term in the original balance?
EV, that's the conversion of mechanical to thermal energy from unit ops. And F is the friction factor, 2 is the number, L is the length of the valve, D is the diameter of the valve, and U is that average velocity, is that U1. Okay, so I want to look at, so I'm going to ignore the kinetic energy, the difference in the kinetic energy. I'm going to ignore the height because I'm going to assume this is horizontal, and I'm going to ignore the shaft work. And so therefore I'm going to get, I think there's a minus sign here, 2FL U squared over D is equal to delta P over rho. I'm going to approximate this by just by the difference of delta P over rho. And there's a minus sign somewhere. It's either here or here, and I forgot exactly where. I don't want to really worry about that too much. But let's solve for u. U is equal to delta p over rho, square root. And then I have a d over a square root of d over square root of 2fl. And typically I'm interested in the volumetric flow rate. So volumetric flow rate V, volumetric flow rate, is the average velocity times the cross-sectional area. So that's an A times that. And this D, again, it's the diameter here. Often we can call that the valve position. And the valve position in your textbook, we're going to replace by pi as the valve position. So we can notice that V is equal to all this stuff. It's proportional to the square root of D. And I want to linearize that. So V is equal to V steady state. So before I change the valve position, plus A square root of delta rho, delta P over rho, square root 2FL, and I want to linearize the square root of D. So I take the derivative with respect to D, and I get 1 over 2 square roots of D. But now I've changed D to pi, steady state, times pi prime. So this thing we can call V prime, and we have V prime is equal to some K valve, but this whole thing is K valve. K valve times pi prime. And therefore, G tilde of the valve, which is equal to V prime tilde over pi prime tilde, is just KV. And that's something we're going to keep using, so I figured it was worth deriving. So we just derived how, what the G, the transfer function for a valve is, that tells me how to go from the position of the valve, the change in the position of the valve, to the change in the volumetric flow rate through the valve. Okay, so why don't we now go ahead and just set up our little example. So this is an example, nothing fancy here. 3 CSTRs in series. But I'm going to have something a little more interesting here, slightly more interesting. That is, I have the volumetric flow rate VB and XAB. So most of the flow rate is going through, coming through B. But sometimes, if I don't like what's coming out here, I have a little valve here where I have an XAA and a VA. So I have a high concentration, a much higher concentration, the mole fraction, of A in the little A stream than in the B stream. So if the value out here isn't high enough, I can spike the feed this way. And so typically I'm going to measure say either XA3 coming out from reactor 3, or if there's a reaction, I might look at a product coming out of 3. And if I don't like that value, I might then do some control on spiking the feed. So that's the basic idea. So we can have a first order reaction or not have a first order reaction. So we've done, except for the control part, we've done this a million times. So I'm going to run through that relatively quickly. So for each reactor, well, before I do that, let's note what is the XA coming in here. XA in. So XA in is the weighted average of XAB and XAA weighted by the volumetric flow rates. So it's VA XAA plus VB XAB divided by VA plus VB. So that's what's going in. It's the weighted average of these two. But we are given that XAA is much, much bigger than XAB. So the B stream may be coming from another part of the plant where A is relatively low in concentration. But just in case, we've got a barrel of almost pure A here, which we can spike if XAB gets too small. Similarly, and since this concentration is so much higher, VA, I never need a big amount of VA, is much, much less than VB. And that's just going to make things a little easier. Well, let's notice the things that are changing. So I may have a disturbance to XB. So XB changes, and my manipulated variable is VA. So let's look at the things that change. Where's my blue chocolate? It's higher. Thank you. Okay, so let's look at the things that change. Well, VA can change, and XAB can change. XAA doesn't change, VB doesn't change. So those things change. So therefore, I have nonlinearities, because I've got a VA in the denominator, and as well as stuff in the numerator. So let's just linearize XA in, because I'm going to want to linearize stuff. So XA in is equal to its value at steady state. Steady state means before I've changed XAB or VA, plus. So now we need to take ddVA times VA prime, the derivative with respect to VA. So I've got VA in the numerator and the denominator. So what's the derivative rule for a quotient? F prime G minus FG prime over G squared. So I've got VA plus VB squared. F prime, the derivative with respect to VA is just XAA. Times VA plus VB. Minus FG prime. F times G prime. G prime is 1. So I've got VA XAA, VB XAB. And I can notice that VA XAA cancels. And this thing just becomes VB times XAA minus XAB divided by VA plus VB squared. And this is all evaluated in steady state from the VA prime. Plus the derivative with respect to XB. Well, that derivative with respect to XB is just this over this. So it's just VB over VA plus VB steady state times XB prime. And if I subtract this from both sides, this is just equal to XA in prime. So, and let's just notice what happens in this approximate circumstance. So this thing I can call alpha. I can call that alpha. But let's notice that alpha, which is VB XAA minus XAB over VA plus VB squared. Well, if VA is much, much less than VB, then the denominator is just more or less VB squared. And if XAA is much bigger than XAB, then the numerator is basically just VB XAA. And these cancel, and this is about equal to XAA over VB. So that's the approximation. Similarly, if I call this beta, beta is equal to VB over VA plus VB at steady state. This is, of course, all the steady state. And this thing is about equal to, because VA is small compared with VB, this drops out and this is about equal to 1. So those are pretty much about what they're equal to. So in that case, we have that XAN prime is very equal to alpha VA prime plus beta XB prime. And that's about equal to XAA over VB steady state VA prime plus XB prime. And now let's just take Laplace transforms. So I have G, I'm going to call this a G, is defined as XA in prime tilde over VA prime tilde, alpha. And this is how V A influences XA in. And G for how XAB influences XA in prime is just equal to beta. Well, let's define it. It's XA in prime tilde over XB prime tilde. And that's just equal to beta, which is about equal to 1. So I've found a bunch of G's. I know GV, I know this G, and I know this G. So those I'm going to need. I'm going to need those. And now I can go and look at my reactor. Any questions so far? Questions so far? Am I the only one who's hot in here? Okay. So for each reactor, what I'm going to do is I'm going to do the algebra as if there's no first order reaction, and I'll just fix it at the end to make the algebra a little easier. I've done the algebra with the first order reactions. So for reactor I have V dxi dt is equal to VA plus VB, because that's the total volumetric flow rate, times XAI minus 1 minus XAI. And so where XAI minus 1 is what's coming in, and XAI is what's going out to reactor I. And let's just notice that what I've assumed, we're given that V1 equals V2 equals V3, and the density doesn't change. So therefore, I don't need a subscript on the V, and the density doesn't change. So the volumetric flow rate into the first one is the same as the volumetric, all the other volumetric flow rates. If they change, we just need subscripts. So I'm not going to worry about that. Okay, so let's divide through by V. And let's linearize. So let's notice what can change here. Well, VA can change, and each of the x's can change. The x's change because once I change what's going in, either by changing the XAB or changing VA, I change what goes out. So all the x's can change, and VA can change. So clearly this is nonlinear, so I need to linearize. So linearize. I have the xi dt is equal to VA plus VB over V steady state, XA I minus 1 minus XAI, steady state. And then I have plus the derivative with respect to VA. Well, when I take the derivative with respect to VA, I just get a VA prime. I'm sorry, I just get this thing. So I have XAI minus 1 minus XAI at steady state over V. times VA prime. Derivative with respect to VA times VA prime plus the derivative with respect to each of the xi's times that prime. So I've got VA plus VB over V steady state times XAI minus 1 prime minus XAI prime. So notice what I did is I took the steady state value, I took the derivative with respect to VA, which was this over this at steady state by VA prime, and I took the derivative of this thing with respect to each of the x's, which gives me this at steady state times that, plus nonlinear terms. And now let's look at the steady state value, or the value at t is equal to 0. So I have dxi steady state dt, and that's just equal to VA plus VB over V steady state. XA I minus 1 minus XAI steady state. Because it was steady state. So I subtract, and I have the XAI prime dt, where the prime is the value minus the steady state, or minus the value of t equals 0, if it wasn't steady state. These terms cancel, and what I have is VA plus VB over V at steady state. I can just call that 1 over the time constant, 1 over time. This is at steady state times XA I minus 1 prime minus XA I prime. And then I have this thing, XAI minus 1 minus XAI over V steady state on VA prime. So all I did is I subtract. Now let's notice that these guys can change a lot. VA only changes a little. So usually, VA is so small, I usually neglect VA, and remember, VA prime is probably going to be much smaller than VA when it's compared with something big. The only time I care about VA is when it's multiplied by something humongous. XAA is really big. So this term is not negligible compared to this because XAB is small and XAA is large. So that makes this product comparable to this product. But over here, since this quantity is not necessarily that big because it's the difference of the x's, and VA prime is really tiny, that's going to be small compared with this, presumably. So I'm going to neglect this. Do I have to neglect it? No. But I'm going to neglect because when VA prime is not multiplied by something big, it's really small. Okay, so let's go ahead, and I have the XAI prime t plus 1 over tau XAI prime tilde prime is equal to 1 over tau XAI minus 1 prime. Now, if I had a first order reaction, rather than me repeating all that algebra, if I had a first order reaction, this would be a T, and this one would be a tau. So if I have a first order reaction, we did that already, I just didn't want to repeat it, where T is equal to tau over 1 plus K tau. And so now I can go ahead and I can Laplace transform. So here I have S XA I prime tilde, because they're prime variables, so the initial condition is 0. And when I take the Laplace transform of the derivative, I get S times that minus the initial condition, which is 0. Plus 1 over T XA prime tilde is equal to 1 over tau XA I minus 1 prime tilde. I factor out S plus 1 over T. I multiply top and bottom by T, and then I have 1 plus plus st over t. Now I multiply that out. I have x a I prime tilde over x a I minus 1 prime tilde. And I'll call this g sub I. So it's this guy over this guy. So I just take t over tau over 1 plus st. Where t over tau is 1 over 1 plus t. Tau divided by 1 plus st. Now this is for 3 reactors, for one each reactor. So in particular, G for the process, well, why don't we jump ahead? XA3 prime tilde is equal to XA3 prime tilde, XA2 prime tilde, XA2 prime tilde, XA1 prime tilde, XA1 prime tilde over XA in prime tilde. And so this thing, each one of these is 1 over 1 plus a tau cubed, that over 1 plus st cubed. And now if I want xa3 prime tilde, I don't really want it divided by xa in prime tilde. I would much prefer it divided by, say, va prime tilde or xab prime tilde. So, but I know what those guys are. So I know from here that if I multiply by xa in prime tilde over va prime tilde, I get g for how va prime affects xa3 prime. And that's, I just multiply that here. So this is just alpha 1 over 1 plus a tau cubed over 1 plus st cubed. And g for how xab affects xa3. I just multiply by this, by xa in over xab prime, xab prime. So that's just 1. So that's just 1 over 1 plus k tau cubed over 1 plus st cubed. And this thing your book refers to as just kb. Or we refer to it as that as well, as the steady state gate. And we've proved that many times. This is the steady state gate. But this is what we wanted. We wanted these G's. That was sort of the goal here. And in particular, we might be interested in not just V, but we might be interested in pi. So to multiply by pi, I need to multiply by VA prime tilde over pi prime tilde. VA prime tilde over pi prime tilde. This will give me how pi prime will affect xa3 prime. And that just means I have to multiply by v prime over pi prime tilde, which gives me a kv. So this is equal to alpha kv kp over 1 plus st cubed. So these are all quantities we're going to use. This is an example that I wanted to get to. Let's see, is there anything else I want to derive there? Okay, so let's just notice this is how the disturbance affects the output. So I'm going to call this GD for short. GD. This is how the disturbance affects the output. D for disturbance. And this is how the manipulated variable affects the output. So I'm going to give this one a name also, G, and for the process, GP. So I'm going to call this one GP because it's the process. And this one GD because it's the disturbance. And let's keep that for safekeeping. We're going to use that within the next few minutes. Let's just give ourselves a little bit of a note of what's going on. So if we go back to these errors here, if my control variable is doing something, then let's remember what my manipulated variable is doing. In order to counteract that my manipulated variable, when this goes up, I want to manipulate something to sort of go down. So this is sort of out of phase. When this one goes up, this one goes down. That's something like that. If I look at the integral absolute error, then as this thing goes like this, the integral absolute error is just growing. But hopefully as this goes down, this levels off. Now, of course, if I have control, then the error is going to go to 0, but the integral absolute error is going to go to a constant. Okay, so what are my approaches to control? There are lots of ways to do control. One way is no control. Pray. So the one way of doing control, maybe not the most effective, is do nothing and just pray. And leave the control to God. The second way of doing it is to do manual control. When I see this goes up, I turn a knob to play with the manipulated variable. That's a lot of work on my part. I'm not sure I really want to do that. Another method of doing that is on-off control, like the heating in this building. Obviously it's on now and it's too hot, so it should go off, but it's not going off. So you can see the problems. You can overshoot with on-off control. But what we're going to learn here is how to do this continuous automatic control. We're going to have a controller that monitors the error, any or all of these, and then automatically, without me doing anything, because it has an algorithm, manipulates the manipulated variables for us. And of course, we always want to have an emergency control on top of that. If something goes wrong, we don't want the plant to blow up, kill people, and destroy the environment. So we have some sort of emergency control. Okay, so any questions? So the most popular controller, and the one we're going to concentrate on here, is the PID controller. PID stands for proportional integral derivative. So it's the PID controller. And that's the most popular controller. And it's been around since the 1940s. Since the 1940s. Remember, in the 1940s, they didn't have really fast computers then. In fact, until von Neumann in the early 50s, they didn't really have what we would even call a modern computer. They had calculating machines. They used some computers in the design of the Manhattan Project, but they were calculating machines more so than computers. All modern computers have what's known as von Neumann architecture, after the genius mathematician John von Neumann, a Hungarian mathematician who had immigrated to the United States. And von Neumann made fundamental contributions in so many areas it's hard to state. As a hobby, he invented mathematical economics. He wrote the foundational book of the mathematical foundations of quantum mechanics, where he took the stuff that the physicists were doing and put it on real mathematical foundation. He was originally a logician and proved many theorems in logic. And he also took the abstract theory of Alan Turing. You may have seen the movie about Alan Turing, about abstract what a computing machine would do. And he designed and actually built, soldering together vacuum tubes in Princeton in 1952 or 53, the first modern computer. And all the computers today use the von Neumann architecture. So they don't use vacuum tubes, but the architecture of how you build a computer so that it can accept programs, complicated programs, is all due to von Neumann. He was also on the Nuclear Regulatory Commission, and he was really one of the geniuses in the Manhattan Project. and he died, I think, at 57. So he did an awful lot. Anyway, that was John von Neumann, if you ever want to look up someone who was, you know, a real landmark person in the 20th century. One other little story about John von Neumann, he, okay, this is important to say, because even though he got his PhD in mathematics, in logic, his father was a banker, and his father did not think mathematics he'd be able to make a living. So his father made him get an undergraduate degree in chemical engineering, which at the time was called industrial chemistry. So we can claim him as one of ours. The thing was, he did his degree in Budapest in chemical engineering, and just 3 or 4 months later, he submitted his PhD thesis in Göttingen in mathematical logic. So doing the PhD obviously wasn't too difficult for him. It only took him a couple of months. But we can claim him since his undergraduate degree is in chemical engineering. He never worked in chemical engineering. And actually, that was quite a common thing in Budapest before the war. A lot of the people who ended up being great mathematicians or physicists got their undergraduate degree in chemical engineering because they came from upper middle class families who didn't think that those were very good careers, that chemical engineering would be better. So a number of people of those great Hungarian physicists and mathematicians had their undergraduate in chemical engineering. One of them, I don't know why I'm telling stories today, I will get back to this in a second. Another one of them was Leo Szilard. Szilard, S-Z-I-L-L-A-R-D. I don't know if you may not never have heard of him, but there was a famous letter that Szilard and Einstein wrote to Roosevelt in, I think, 1941, saying, there's the possibility of developing a nuclear weapon. We don't want the Germans to do it first. We need a project to build it here in the United States first. And that was Szilard and Einstein wrote that letter. Szilard is also, he was a physicist, but his undergraduate degree was in chemical engineering. When it came to building an atomic bomb, there's a problem. You need a chain reaction of nuclear events. So what you need is, if a fission bomb, you have a nucleus that essentially falls apart, it decomposes, fissile, and sends out, among other things, neutrons. And the way you get one of these unstable nuclei to fall apart is it has to absorb a neutron of just the right energy. If you had a little bit of quantum mechanics, you'll know that if it's not the right energy, it won't be absorbed, if it's too much or too little. Well, to get a sustained chemical reaction, nuclear reaction, the neutron that is emitted when one nucleus is fissile has to be of the right energy to excite, to make the next one fall apart. If not, you won't have a sustained nuclear reaction. But naturally, the neutron is of the wrong energy. So what you need is a moderator. What a moderator is it absorbs a fast neutron and puts out a slower neutron. Absorbs a neutron and puts out a neutron, and you want it to absorb the neutron coming out of the fissile uranium and emit another neutron that's just the right energy to blow up another uranium nucleus. Well, nuclear fission was discovered before the war by Otto Hahn, who was a German physicist. And by theoretical calculations that many people had done, there were only two possible moderators for uranium. One of them was heavy water, D2O, and the other one was graphite. Obviously, you'd rather work with graphite because D2O, deuterium is present naturally at less than 1% concentration in water. So in order to get enough D2O, you need multiple distillations. So everyone wanted to work with graphite. So Otto Hahn did the experiment with graphite, and it didn't work. Couldn't get a sustained reaction. So the German bomb project, which was run by Heisenberg, turned its attention to heavy water. And you need a lot of energy to do these multiple distillations. And during the war in the Third Reich, the only place with enough energy to do multiple distillations were the natural hot water geysers in Norway, in occupied Norway. And the Norwegian partisans did a very good job of blowing them up on a regular basis. So that's why the Germans never got the bomb. Because, now, everyone knew Otto Hahn's work because it had been published. So the head of the experimental part of the bomb project in the United States was Enrico Fermi. Oh, by the way, Heisenberg was the head of the bomb project in Germany. He didn't try graphite again because Otto Hahn was the expert, and Germans respect expertise. So he accepted that and only tried with heavy water, and he failed, luckily. Enrico Fermi was Italian physicist whose wife was Jewish, so they emigrated to the United States before the war to get away from Mussolini. And he also knew Otto Hahn's experiment, but he didn't respect authority. He said, let's figure it out. So he tried Otto Hahn's experiment and it didn't work. Graphite didn't work. But instead of giving up, he went down the hall to Szilard, who was also at University of Chicago, or Fermilab, where they were. And Szilard was a chemical engineer, like you guys, his undergraduate. And in those days, chemical engineers knew how to make stuff. That's what chemical engineers did. So he went to Szilard and he said, Leo, how do you make graphite? Do you just dig it out of the ground? And Szilard knew because he had done his design class. So he told him how you do it, and part of the process of taking raw graphite and turning it into graphite is you use boron. And as soon as he said boron, both he and Enrico Fermi understood that that's why it didn't work, because boron absorbs neutrons like crazy and doesn't emit neutrons. So even if you had trace amounts of boron in there, you would kill the reaction. So the two of them sat down with Szilard, mainly Szilard, and they designed a process for refining graphite that didn't use boron. And they tried the reaction, it worked, and that's why the United States got the bomb, thanks to the chemical engineers. That's the moral of the story. Okay, enough stories. Now let's get back to the PID controller. Why is the PID controller interesting? The PID controller there are many issues in control. There's an issue of stability, of frequency response, of tuning and performance. What's the one goal is we want the error to go to zero, no offset. How do I know what no offset means? And when I want to look at offset, I want to know that the limit as t goes to infinity of E of t is zero. Well, we know from the final value theorem that that's the same thing as the limit as s goes to zero of s e tilde of s. I want that thing to go to zero. And for the PID controller, you can show that this is indeed the case. And that it's the case for a pulse disturbance, for anything that looks like a step disturbance, even if it's continuous, and even sometimes for a ramp disturbance. So those are one great feature of the PID controller. Another feature is that it's widely applicable. Well, that's insensitive to error. What does that mean? Every time we write down a model, models are imperfect. So for example, when I wrote down the CSTR model, I assumed that each CSTR was perfectly mixed, instantaneously. As soon as a drop of fluid comes in, it's instantaneously mixed. That can never actually be true. And then I linearized the model. I didn't take the whole model, I linearized it. That's also an approximation. So all models are approximate. The nice thing about the PID controller is it's insensitive to small model errors. So these little errors due to these approximations, the PID controller can overcome them. It's widely applicable. You can use it in many different situations. It can be tuned. It has a few parameters in it. So you can use it for very different situations just by tuning the parameters, which we will talk about. And finally, there are enhancements. You can make it more complicated if need be. So why don't we get down to brass tacks? First, let's look at what the control loop is. So let's look at the control loop. The control loop, I have a set point, SP. And what I want to do is I want to take SP and I want to subtract the value of the control variable. set point with a plus and subtract the control variable, or at least the measured value of the control variable. And that difference is the error. Now the error, now of course that's the actual error, and of course once I have EFT, the controller can calculate the IAE, the ISE, or the ITAE. Once I know EFT, I can plug into here and calculate it. So let's assume that's all in the controller. So then I have a GC, the controller, and the controller takes in the error and spits out the manipulated variable. And that manipulated variable, so for example, the manipulated variable may be the position of the valve. May tell me the position of the valve. So I need to know how the valve, GV, how that changes the position of the valve into the volumetric flow rate, into VA. So I need to know how the position of the valve gives me VA. Then that goes into the process, GD. It's going into the process, VA, and then what comes out is, in this case, it's the control variable. But I might also have a disturbance. And that might go to GD. Disturbance also affects XA3 prime. So I might add, because I might have the effect of the disturbance as well as the effect of the control. And what comes out is the control variable, CAV prime. But now I have to measure the CAV prime. So S is, what does S stand for? Detector or something? S, sensor. Sensor. This is valve, sometimes called final element. And this is the control loop. Now I want you to notice, this is called closed loop control, or loop, because there's a loop here, it's a circle. If I want to make an open loop, I just break it here. Or I break it here. Or here. There's an open loop, I just have the process. Control loop means I have a loop. And what we'd like to do is come up with CV prime tilde as a function of D prime tilde, or as a function of SP prime tilde. So now I just Laplace transform everything. Notice, if this is CV prime tilde, this is CV prime tilde. And this is CV M prime tilde. Is the picture clear? Is the picture clear? Okay, so let's go through. I'm going to need help here. CV prime tilde. I have a plus here. So can someone tell me what CV prime tilde is in terms of things that I know, D prime tilde or MV prime tilde? And or?
It's the sum of D prime tilde and
The sum of what?
the sum of that, yeah.
So what is this here? What is this equal to?
So that would be D prime tilde times
GD. Okay, so I've got GD times D prime tilde plus something. And what is that plus? That's, I want to relate it to MV prime tilde. What is that equal to? Somebody else? Let's have some volunteers. This is not hard, we did this before. Do you want me to call on people? If you don't volunteer, I'll call on people. I'll count to 3 for a volunteer. 1, 2, 3. You answered already. Okay? How about in the back?
GP plus GE times.
Wait, GP
GP times GE
times GV
times
Why didn't you just volunteer? You knew the answer. Don't be shy. Okay, so now I want to relate mv prime tilde to e tilde. What is mv prime in terms of e? How about in front of him? I can't hear you. It's e, so this thing is gc times e prime tilde. What is e prime tilde equal to? How about next term? What is e prime tilde? Minus. So this is equal to gc times sp prime tilde minus cvm prime tilde. And what is cvm prime tilde equal to? How about behind her? Robbie? What is cvm prime tilde in terms of cv prime tilde? So this is gs times cv prime tilde. So let's rewrite that. I've got cv prime tilde is equal to gd d prime tilde plus gp gv gc times sp prime minus gs cv prime tilde. And notice I've got a cv prime tilde on both sides. So I need to take this term, move it to the other side of the equation, and divide out. So I get cv prime tilde is equal to, it's equal to d prime tilde times gd divided by something plus sp prime tilde times the ratio. There, I've got a gp, gv, gc. But now I take this term, bring it to the other side of the equation with a plus, factor out everything, and divide by the 1 plus. So I've got 1 plus gp, gv, gc, gs. 1 plus gp, gp, gc, gs. And this now is, from the block diagram, this is the solution. And I want you to notice that this over here is G for how D affects CV prime. And this thing is the overall G for how ST prime affects CV prime. What does that mean? I can have a change in the set point. Maybe the specs on the product aren't good enough, so I change the set point. What's going to happen? Or I could have a disturbance. There are many disturbances that are allowed. Let's see, we'll see what happens. I want you to notice that the stability of the system and all the questions about stability all depend on the denominators of these G's. And notice the denominator is 1 plus something. That's because it's closed loop, the 1 plus. And I want you to notice that the denominators are exactly the same whether or not I have a disturbance or a change in the set point. It's the same denominator. So the stability of the system does not depend on D prime or SP prime. It depends on the denominator of the G's. So the stability of the system depends mainly on the denominator, and the denominator is the same for both of these. Any questions on that? Questions? Okay, so now we're ready to look at a particular mode of control. Let's look at the proportional mode, just proportional control. That says mv prime of t is defined as, is just proportional to E prime of t. plus some sort of offset, plus a constant. So what does that mean? That says if I have a certain error, then I have proportional control. I'm going to change the manipulated variable proportional to the error. Now what is IP? IP is just a number. And I set this number so that when the error is 0, the manipulated variable it doesn't change. So this just makes the initial condition 0. So let's Laplace transform. So if I Laplace transform, I'm sorry, that's MV, not MV prime. So there's no primes. So let's look at steady state. So in steady state, MV steady state is Kc E, or if you like it, T equals 0. And if I subtract, I get MV prime is equal to Kc E prime. So the IP's cancel. And when I Laplace transform, I get G of the controller, which is what I need here, GC, which is MV prime tilde over E prime tilde, is just Kc. It's just a constant. For proportional control, it's just a constant. Okay, so if it's a constant, let's see what we can do here. Let's do the analysis for this particular problem. Let's look at the control variable for this example. So here's the example. And let's do it for GD. So let's go back to the 3 CSTR example. And let's calculate GD. Or, let's calculate this guy. So G of D goes to CV prime. That's equal to GD. Well, we said we know what GD is. Where did GD go? Here it is. It's KP over 1 plus ST cubed divided by 1 plus GP. Well, GP we said is this. So it's alpha KP 1 plus ST cubed. GV we said is KV. GC, we just said that's KC for proportional control. Times GS. I'm going to assume GS is 1. So there I have D prime. I need a little more space. Have you taken pictures? Or do I have to squeeze here? I guess I'll squeeze here. Continue. So we don't have a lot of time. Okay, so what I'm going to do is, to make sense of this, I'm going to multiply by 1 plus ST cubed. So G of D to CV prime is equal to KP divided by alpha KP KV KC plus. And what am I plussing? I'm plussing 1 plus ST 1 to the cubed. That's all in the denominator. And I want to get to some result here, and let's see what the result is. Let's say I want to know what happens. I would like to look at this one. Let's look at the limit as S, and I'm going to let D prime be equal to a step. So D prime tilde is delta D over S. So let's look at CV prime tilde. Let's look at CV prime of t, the limit as t goes to infinity. That's the limit as s goes to 0 of s CV prime tilde. That's the limit as s goes to 0. This thing is g times d prime tilde. Okay, so I've got an s, and let's do the d prime tilde. Delta d over s times the g, and the g is all this. So the g has got a kp over alpha kp, kv, kc plus 1 plus st cubed. And let's take the limit as s goes to 0. You don't have to write every word down. Listen, it's being recorded. Cancel the s. Take the limit as s goes to 0. As s goes to 0, this term is 0, so I just have 1. And that limit is delta d kp over 1 plus alpha kp, kv, kc, and that's not equal to 0. That is not equal to 0. So notice the limit of CV prime as t goes to infinity is not 0. The change in CV prime does not go to 0. So what is that telling me? That's telling me that I have an offset. I have an offset because the limit of CV prime as t goes to infinity is not 0. So that tells me that proportional control alone is never good because I'm always going to get offsets. It may be good in combination with other control, but in and of itself, it's not good. Now, why is that? Let's just think for a second. Let me just finish the sentence. Why is that? For the controller to go on in proportional control, for the controller to do anything, I need there to be an error. If the error were 0, if the error were 0, which is what I want the error to go to 0, then the controller is not doing anything. But there was a disturbance. How can the manipulated variable be the same thing it was before the disturbance and have no offset? Because if I get to error 0, this is 0, the manipulated variable is not doing anything because it's just proportional to this, if you like. It's only proportional to it. And that can't be right because that value of MV worked when there was no disturbance. Now there's a disturbance. It has to be doing something. So that's why there's an offset. Question?
So this limit for the offset that you found, if you plug in the numerical values for k values, does it give you the actual
Yes.
value of the
Yes.
offset?
Yes. Yes. Question? I spent too much time telling stories today. Okay, but we will go on and do another example with proportional next time. Well, next time meaning after the exam. And then we will also do the integral. We'll look at the integral controller alone, the differential controller alone, and then we'll put them together. Question? Okay, for those who couldn't manage to get here on time, the exam is Wednesday. We're going to start early at 10:15, like last time. Hopefully you understand now what boundment means. You can bring your textbook, your class notes, nothing else, no homework solutions, no other solutions from the internet, just your textbook and just your textbook and just your class notes. They have to be properly bound. Bound does not mean you staple 3 pages together and staple another 5 pages together and another 6 pages together. Bound means in a binder, like a loose leaf, or some other way that it's one device that I can pick it up and shake it and nothing falls out. Okay, I hope that's clear. And how many people are we today? 2, 4, 6, 8, 10, 12, 14. So again, we're missing on the order of 9 or 10 people. Yes?
We talked about doing like an afternoon.
Yes, so we'll do it tomorrow, say 4 o'clock, is that reasonable? So we'll have, and we were going to do that here or online? Okay, so tomorrow at 4. Other questions? Okay, yes?
Are we allowed to have like a sheet, like a study sheet? that-
Yes, you can have a page, not 20 pages, you can have a page where you summarize all your notes, use as an index or a fun thing. That should be bound as well. And you could have obviously the cost transfer table being bound.
So there was a class where we discovered that there were 2 separate
You can use either one.
laws. But would
They have the same material, they're just
They
rearranged.
don't have the same material. The example that we did in class, that specific example, the solution that we found in
So you
class
can have
was
both.
on our table. Like, would it be possible to somehow get a copy of that other one in case whatever we need on the exam isn't on the table that we have? Because what we did in class wasn't on our table.
Okay, I'll just have a copy on the desk if you need it. I think you have the one that's page 110, not the one that's page 100. So I'll just have a copy on the desk, no problem. Anything else? Okay, so we'll have this review session on Wednesday, I'm sorry, tomorrow at 4 o'clock.